Hello everyone, and this is Dr. Hemangusdi Harma, Assistant Professor, Department of Physics, Morunga College. Today we are going to discuss about scalars and vector fields. In this talk, we will have a basic introduction of the scalar and vector fields. Apart from them, we will have the idea of the gradient, divergence, and curl. Prior to enter the depth of the topic, let's have the basics of the physical quantities. Physical quantity is a property of a material or system which can be measured or quantified. Physical quantities can be expressed in terms of value, consisting of a numerical value and a unit of measurement. Scalars are a special type of physical quantities which have only magnitude and there is no question of any directions. Interestingly, scalars remains unaffected upon any alteration of the vector space basis, that is a frame of reference. Similarly, vectors are also a kind of physical quantities which is unlikely to scalars and have both magnitude and directions. Vector usually modifies upon any alteration of the vector basis space as a frame of reference. Force, displacement, electric field, etc. are some examples of the vectors. Now we will have the basic idea of the fields. Suppose we have a positively charged body. This can exert force on any other charged particle up to a certain region around its existence. The space can be treated as a field for this positively charged body. There is some other example where we can place a hot body, that is a body in a high temperature. The temperature, if we note the temperature around it, we will get that the temperature falls down almost monotonically as we move apart from the body, and up to a certain region we will have a mapping of a different temperature value at different points. The region where the existence of some body or something can be filled, that can be interpreted as a field. If it is in terms of vectors, we will term as a vector field. If it's in terms of scalar quantity, then we will have a scalar field. So let's have a basic definition. So the scalar field is defined as the way how a scalar quantity is distributed over space. To be more specific, a scalar field associates a single number to each point in space. For example, the variation of temperature over the space around a candle. Suppose we have lighted a candle, and if we note the temperature around the candle, then we will have different temperature values around it. And all the sets of temperature at different location over space may be termed as the scalar field of temperature. Similarly, the mass distribution in different layers of the earth crust can be also considered as a scalar field. Now coming to vector fields, vector field is defined as the way how a vector quantity is distributed over space. To be more specific, a vector field associates a set of vectors to each point in space. For example, the electric field over space around a charged particle. Let's have the basic introduction of the operator del. It is a differential operator and is of course a vector quantity, vector operator. So in Cartesian coordinate system, the del operator can be expressed as del equal to I cap d by dx plus j cap d by dy plus k cap d by dz, where the x component, y component, z component can be expressed like this. The interesting part of the del operator is that the nature of the scalar field or vector field can be interpreted after operating with it. So let's have it. So let's discuss about a gradient of the scalar field. This is nothing but the operation of the del operator over a scalar field. The gradient of a scalar field is a vector field. That is, if we operate del operator over a scalar field, we will get a vector field. That the point in the direction of the nearest rate of increase of the scalar field. The magnitude is the rate of change and which point in direction of the greatest rate of increase of the scalar field. For example, the temperature gradually drops as we move away from the candle. So there is a gradient of temperature. Mathematically, gradient of temperature or gradient of any scalar quantity, that is phi, can be expressed as del of phi. So we can interpret del phi as I d by dx plus j cap d by dy plus k cap d by dz of phi. So after simplification, we are getting a vector field. That is, divergence of any scalar field is nothing but a vector. We will have a basic example here. So we are taking a scalar field, that is phi equal to x square plus xy cube. Upon operation of the gradient, we will have the basic expression like this. After inserting the phi value from the equation, we will have this, and after simplification we can write like this. So one point to be noted for a student point of view, as we are differentiating with respect to x, we are keeping y and z constant. As we are differentiating with respect to y, we are keeping x and z constant, and as we are differentiating with respect to z, we are taking x and y constant. In the last term, we can note that there is no z term and there is only x and y term. So this will term, there will be no result. This term will be vanish basically. So after simplification, we are getting like this. Some assignment is also introduced for students, which they can submit to my mail ID, or they can submit via offline to the department also. Let's start the divergence of a vector field. In the earlier we have discussed the gradient of a scalar field. So it's in physical world or in physical term, the divergence of a vector field is the extent to which the vector field flux behaves like a source at a given point. In simple work, it is a measure of outgoingness. A point at which the flux is outgoing has a positive divergence and is often called a source of the field. A point at which flux is directed inward has a negative divergence and is often called a sink. Mathematically, the divergence of a vector field A can be expressed as the dot product between the del operator and the A. That is, we can simplify like this. If A vector equal to I cap A1 plus J cap A2 plus K cap A3, then divergence of A can be expressed as and simplifies as del A1 by del X plus del A2 by del Y plus del A3 by del Z. That is, this is a scalar quantity, and this and the dot product between del and A vector, that is the divergence of any vector field, we are getting a scalar. If the value of this scalar value is positive, then we will have the source field, and if it's negative, then we will have a sink field. That's a simple. So we are taking an example here. We are taking a vector field A equal to I cap x square plus k x y cube. We have to find a divergence of it. So as per formula, we have put in like this and inserting A from the equation, and after simplification, we are getting d by dx of x square plus d by dz of x y cube. So here this term is independent of z, and y and x are constant for z. So we will get 0 for this term, and we are getting twice x for this question, for this vector field. Divergence of A equal to twice x. Some additional questions or have been placed for students. They can solve it, or if they find some problem, they can consult me. Now coming to the curl of a vector field. In vector calculus, the curl is also known as a rotor, is a vector operator that describes the infinitesimal circulation of a vector field in a three-dimensional Euclidean space. The curl at a point is a field is represented by a vector whose length and direction denotes the magnitude and the axis of the maximum circulation. The magnetic lines of force shows a rotating nature which yields non-zero curl. Mathematically, curl of a vector field A is represented as the cross product between the del operator and A. So after simplification, we'll have an expression like this. So please note that curl of any vector field is also a vector. So we will have some problem. Let's have some example of it. The question is that to solve that, the curl of a position vector is 0. So we have the position vector to any arbitrary point x, y, z can be represented as r vector equal to I cap x plus j cap y plus k cap z. And if we take the curl of it, we can represent in terms of matrix form like this. So this will yield almost 0 because z is independent of y and x is independent of z, and like that. So we can conclude that the curl of a position vector is non-solenoidal. So some questions have been placed for students, so they can solve. So in the next class, we will discuss physical examples and applications, and we will solve more problems regarding this. So for today, for this class, we are concluding our lecture. Thank you everyone. Thank you for listening. For students of a college, or as this is a flip classroom, flip class, so we request to solve the questions addressed here and submit to my mail ID, or they can submit offline after solving to the department within 1 week after receiving this video. Thank you everyone.